In this class, we will continue our discussion of the Factorial Anova by exploring further the example we discussed in the previous class. Please refer to those data as needed to help your understanding during this class. Now, let's consider what happens in a Factorial Anova by looking at the summary table. First, let's look in the source column to the sources of variance in a Factorial Anova. As in one-way Anova, total variance is partitioned into treatment and error variance. But the treatment or between subject variance is partitioned further in a factorial design. We have a treatment effect associated with the type of treatment independent variable and a separate treatment effect associated with the marital adjustment independent variable. We call these effects of treatment and of marital adjustment main effects. They represent the effect of one independent variable without reference to the other independent variable. In that way, they are similar to what we would have found if we had done two separate one-way analysis of variance. We compute the variances for these effects by analyzing how the means in the margins or outside the cells vary from the grand mean. A new term is also partitioned from the treatment or between subjects term, and that is the interaction effect. The interaction is the joint effect of the two independent variables on the dependent variable, and it is analyzed by considering how cell means vary from each other. The error, or within subjects term, is once again computed by analyzing how individual scores on the dependent variable deviate from the mean of each cell or each group. Let's continue our look at the summary table by considering how degrees of freedom are computed. Degrees of freedom total remains n-1. So if we had 5 participants in each cell, n-1 equals 45 minus 1 equals 44. Degrees of freedom for the treatment term equals cells minus 1, or 9 minus 1, equal to 8. As in one-way Anova, degrees of freedom for main effects are related to the number of levels for each independent variable. For the type of treatment factor, degrees of freedom equal k minus 1, with k equal the number of levels of that independent variable. Because k equals 3 for both independent variables, their degrees of freedom equal 3 minus 1, or 2. The degree of freedom for the interaction term is computed by multiplying the degrees of freedom for each of the independent variables comprising the interaction. In this problem, that would mean multiplying 2 by 2 and resulting in 4 degrees of freedom for the interaction. Because the degrees of freedom in ANOVA are additive, we can compute the degrees of freedom error by subtracting degrees of freedom for each effect from the total. In this ANOVA, we would subtract 8 from 44 equal to 36. We can also compute error by subtracting the number of cells or groups from n. Here, 45 minus 9 equals 36. We could also compute degrees of freedom error by subtracting 1 from the number of participants in each group or cell and adding them together. In this problem, if there were an equal number of participants in each group, the number of participants in each group would be 5. Thus, 5 minus 1 equals 4, and multiplying 4 by 9 equals 36. From our earlier classes, hopefully you will remember that sums of squares, or SS, is the numerator of a variance. Sums of squares total is computed by summing the square deviations of the score of every participant in the study from the grand mean without reference to their group assignment. Sums of squares treatment is computed by summing the squared deviations of the cellular means from the grand mean. The main effects of the independent variables are computed by summing the squared deviations of the marginal means for that independent variable from the grand mean. The interaction is computed by analyzing the pattern of variation of cellular means from each other. Practically speaking, SS interaction can be derived by subtracting the SS main effects for each independent variable from SS treatment. Finally, SS error is computed by summing the squared deviation of each score from the mean of its group. Please note that the treatment and error sums of squares add to total sums of squares, and that sums of squares for the main effects and the interaction add to the treatment sums of squares. Thus, sum of squares treatment has been partitioned into two main effects and an interaction term in two-way ANOVA. Let's imagine that the numbers that appear in each row of the sums of squares column were obtained in our analysis. We will use these numbers to compute the mean square and the F for this summary table. We next turn our attention to MS, or mean squares. Remember that a mean squares, or the mean of the sum of the squares, is another name for a variance, and it is computed by dividing sums of squares by degrees of freedom. Thus, the mean square for the main effects is computed by dividing their sums of squares by their respective degrees of freedom. Thus, 1200 is the variance associated with the type of treatment, and 600 is the variance associated with marital adjustment. The MS for the interaction term is obtained by dividing its sums of squares by its degree of freedom. Thus, 750 is the variance associated with the effect of the interaction. Finally, MS for error is computed by dividing sums of squares error by degrees of freedom error. As we complete the summary table, note we have three treatment effects, which is a big departure from the one-way ANOVA, where we only had one treatment effect. We will need to compute a separate F to test the null hypothesis that is associated with each effect. As in the one-way ANOVA, the F ratios are computed by dividing a treatment variance with an error variance, or an MS associated with a treatment effect and an MS associated with error. Before we go to the next slide, see if you can compute the F for each effect in this problem. Hopefully you received the three F ratios listed in the summary table in this slide. To test hypotheses associated with each of these F ratios, we will need to locate the critical value for each F. To use the F table, we need to know the degrees of freedom for the numerator of the F ratio and degrees of freedom for the denominator of the F. For the type of treatment main effect in this problem, the degree of freedom associated with the numerator of the F is the type of treatment degree of freedom, and the degree of freedom for the denominator is the error degree of freedom. Looking on the F table for alpha at 0.05, when degrees of freedom are 2 and 36, we find the critical value is 3.26. Before proceeding to the next slide, see if you can locate the critical values for the marital adjustment main effect and for the interaction effect. The critical value for the marital adjustment effect is 3.26, the same as for type of treatment. and the critical value for the interaction term is 2.63. Now that we have a test statistic and a critical value, we need to discuss the null hypothesis that we are testing in each case, which we will do in our next class.